Hi, I'm Professor Goines, and welcome to the Math Professor's YouTube channel. If you look for videos explaining topics in college mathematics, just go ahead and hit the subscribe button because you're in the right spot. And let's go ahead and get into the current video. This is going to be the fourth video in the following series where we look at the characteristic equation for a constant coefficient linear differential equation. Okay? And this is going to be the case where we look at when I have complex roots to that characteristic equation. So suppose a plus or minus bi, so these two complex numbers, are the roots of the characteristic equation of a differential equation. Now there could be other roots as well, so rather than saying the roots, I could just say these are some of the roots. This of course applies to a second order equation, but you could have a third order equation that has a real root and then two complex roots, for example. And a very similar discussion would suffice there. But this is still going to give me the same type of solutions. So again, suppose I've got these two complex numbers as roots of a characteristic equation for a differential equation. Again, constant coefficient, linear, homogeneous, all the same story. Well, then that would give me the following. I would get y1 is equal to e to the, say, a minus bix. And then y2 for my second solution would be e to the a plus bix. And these two functions would satisfy that differential equation. However, here's the issue. These are complex valued functions. And since you generally discover this or will experience this in a elementary differential equations course, we don't do anything with complex functions. Everything we do is a real valued function. That means I have to somehow manipulate these to get two linearly independent, real valued functions of a real variable, right? I have to get everything real, and I also want two that are linearly independent. Well, we have a tool for doing that, and the tool is Euler's formula. So Euler's formula gives me the following. E to the I theta is cosine of theta plus I sine of theta. Okay? And this is going to give me a connection between converting an exponential function to trig functions. And then I can manipulate those to just extract sort of the real parts of that. Here's how this is going to work. Well, y1, let me separate this here. y1, I can write that as e to the a, and then e to the negative bix. And using Euler's formula, this is going to give me e to the a, and then e to the negative bix is going to be cosine of negative bx, and then plus I sine of negative bx. Now, cosine is an even function, so therefore cosine of a negative is the same thing as cosine of the positive, and sine is an odd function, which means I can take that negative and I can pull it out as a coefficient, or the sign of the negative is the negative sign. That gives me e to the a cosine of bx minus e to the a sine of bx. Then times I. Don't forget the I. This then would be another way to write the solution y1, which is equivalent to this function right here. Now let's look at y2. Using basically the same thing, I just have a positive as opposed to a negative. Once again, this is going to be e to the a, e to the bix, e to the a, and then e to the bix is going to be cosine of bx plus I e to the a sine of bx. Okay? Now, y1 and y2 are both solutions to the differential equation. The problem is they are complex valued. And if you remember, if I have two solutions of a homogeneous equation, then any linear combination of those is also a solution. In particular, suppose I take 1/2 y1 plus 1/2 y2. This is a linear combination of two solutions of the homogeneous equation. Therefore, this is also a solution. Well, what that's going to mean is I'm going to take this expression right here, multiply it by 1/2, and then I'm going to add that to this expression where I multiply by 1/2. Well, let me see. I don't know if I have room to write all that out. Let's see. Well, let's just go ahead and try to do it. I would have 1/2 e to the a cosine of bx minus 1/2 I e to the a, and then times, sort of cheat here, bx, and then that's going to be plus 1/2 e to the a cosine of bx plus 1/2 I e to the a sine of bx. Well, notice that the sine terms are going to cancel. They're the same thing, just opposite sign. And then the cosine terms, there's 1/2 here, 1/2 here, which means I've got a whole one, right? E to the a cosine of bx. That gives me the following for one of my solutions. So I'll denote this as y3 for the moment. y3, which is also a solution of the differential equation, is e to the a cosine of bx. This is a real valued function of a real variable, and it is, again, it's a solution. So we're going to go ahead and box this off. This is one of the ones that we will use. Well, if I look at these two solutions that I have here, again, y1 and y2, the other part of this that I don't have, of course, is the sine part. Well, what linear combination could I take of y1 and y2 to sort of extract just the sine part? Well, I want to be able to cancel the cosine, so therefore I'm going to subtract. So let's see what we would have to do here, sort of piece this together. So I know I'm going to have to do y1 minus y2. All right? y1 minus y2 is going to cancel the cosine terms, but then I'm going to have this positive I, and then I'm going to have, let's see where, oh, sorry, down here, negative I, positive I, so that's going to be negative I minus I, which is going to be negative 2I, and then I have to cancel that. So what I'm going to do is let me divide this by 2I, divide that by 2I, so this would be negative, and then, actually, let's do it this way. Let's do minus and then plus. All right, let's go ahead and then write this out. This would be negative 1 over 2I times y1, so e to the a cosine of bx, and then plus 1 over 2I times y2, or I'm sorry, then the second part of that, which is negative I e to the a sine bx. And then I'm going to add 1 over 2I times y2, which was e to the a cosine of bx plus 1 over 2I, so that's this coefficient, times I e to the a sine of bx. And what does that give me? Well, notice that the cosine terms cancel. As far as the sine terms, I've got negative, negative, which is positive, I over I, which is 1. This is 1/2 e to the a sine bx, and that's the same thing down here, which gives me e to the a sine of bx. And we can call that y4. Again, it's just another solution. Now e to the ax, e to the a cosine bx and e to the a sine bx are linearly independent, and they're both solutions to the differential equation, and therefore linear combinations of these two generate the entire solution space for the homogeneous equation. Notice if I go back to this here, this is just a linear combination of y3 and y4, as is this one right here. All right, so this tells me then how to construct these solutions in the case when I have complex roots. What I do is I get my complex roots, a plus or minus bi, and then I just take the real and the imaginary part, and the real part is the exponent on the exponential, and then the imaginary part is the coefficient of x inside the cosine and inside the sine. Let's go ahead and solve a differential equation using that. All right, let's start with y double prime plus 4y is equal to 0. So let's go ahead and use the characteristic equation, which is going to lead to complex roots, and then we will see how that fits into these solutions. So solution. Okay. Characteristic equation for this differential equation would be r squared plus 4 is equal to 0. And then I'm going to subtract 4, take the square root. I get r squared is negative 4. So r is plus or minus the square root of negative 4, which is plus or minus 2i. And remember at the beginning when I wrote the complex numbers, I did explicitly write them in the form a plus or minus bi. So let's do the same thing here. R is going to be 0 plus or minus 2i. These are the roots of the characteristic equation, which lead to my solutions. Now, over in the initial discussion, you know, I labeled this as y3 and I labeled this as y4. Of course, the subscripts are arbitrary, but generally I'm going to use 1 and 2 for the first and the second solution, and these are really the solutions that we care about because they're real valued functions. And let's go ahead and use, again, y1 for this one, y2 for this one. Again, subscripts are arbitrary anyway. Okay, this gives me e to the 0 cosine of 2x, which of course is just cosine of 2x. And then y2 would be e to the 0 sine of 2x, which of course just gives me sine of 2x. And just by inspection, we could actually solve this. What function do I start with where when I take 4 times the original function and then I add its second derivative, they cancel out? Well, of course, sine of 2x first derivative would be 2 cosine 2x, and then the second derivative would be negative 4 sine 2x. And then, of course, those two would then cancel when I pop it in here. Let's go ahead and do one more example. Let's do one more solution for a differential equation that has complex roots to the characteristic equation. Okay, characteristic equation would be r squared minus 4r plus 13 is equal to 0. Let's solve this. Let's just use the quadratic formula. R would be equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, so 2 times 1. And this would give me positive 4 plus or minus the square root, negative 4 squared would be 16, minus, so then 4 and 13 would be 40, be 52, 2, all over 2. And so I get 4 plus or minus the square root. So 16 minus 52 would give me a negative, so be 36 all over 2. And of course, negative 36 is, the square root would be 6i, so I get 4 plus or minus 6i over 2, which gives me the following roots. 2 plus or minus 3i for my complex roots. And again, the real part being 2, the imaginary part being 3, says that the two solutions for this would be y1 is equal to e to the second cosine of 3x. And then y2 would be e to the second sine of 3x. And of course, linear combinations of this would give me my general solution. In other words, the general solution, if I had, say, initial values, like an initial value problem, where we could solve for c1 and c2, we would use the following function. c1 e squared cosine of 3x plus c2 e squared sine of 3x. Okay. Once again, thank you for watching, and please consider subscribing.